Today we're going to shift gears a little bit and talk about signals and signal integrity, because all of these things that we have talked about in this class so far really impact how signals behave in a circuit. And circuits can talk to each other in a lot of unintended ways, and that's sort of what we're going to talk about today. Signals on circuits that are not physically touching can affect each other, because we've talked about questions like radiation, mutual inductance. That's when you have, one loop of current over here and another circuit over here, and this one generates a magnetic field that creates some flux that goes through this one, and then you have another induced current on the second circuit due to the first one. So that can be interesting, to say the least. You can also have mutual capacitance. Take, for instance, this situation where maybe you have a transmission line, I'm drawing them as microstrip, on a ground plane, and another transmission line near it on a ground plane. They each have their per unit length capacitance between them and ground, which we have talked about before. But if they're close enough to each other, they might have a substantial amount of capacitance between them. And that means that, again, if there's a voltage on this one, you might end up inducing a current on that one. So these sorts of things demonstrate that when two circuits are not physically touching each other and not physically connected, they can still have a pretty strong effect on each other. We're going to talk about some of those effects today and how and why they work. So I think it should be interesting, to say the least. I want to start with an activity, though, that I hope will illustrate one of the major concerns of this phenomenon, which is frequency. So here's your activity. It's about bandwidth. All right. Use Matlab to compute and plot the FFT of a sine wave and a square wave of the same frequency. Now, most of you probably have taken signals and systems already, but if you haven't, what we're looking at here is the frequency content of these two signals, and we're going to compare them because it is actually different. I'm going to write down basically the Matlab commands that I would use to do this. So first thing I'm going to do is define a time variable. I like to put semicolons after all of my lines so that we suppress the output. Otherwise it prints everything to the screen. That's kind of annoying. I am arbitrarily choosing my frequency to be 10. Remember that in Matlab, you would actually have to use the star to do the multiplication, but I'm not writing those down because that's annoying to write. The sine function does what it says on the box. It just literally puts out a 1 if x is positive and a -1 if x is negative. So what I've done here is I've made a vector that is a sine wave at frequency 10 over this time period. And then for this one, I have made a square wave that is just that function. It also puts out 0 if it is equal to 0. So if the sine wave has values that are exactly 0, those values will come out to be 0 here in y as well. Then we can define some FFT values. Trying to write down this frequency variable in the most efficient way. There. Take a screenshot of this. You need it. Then make plots of these two things versus frequency. If I did this right, these should be the same length. These FFTs and this frequency variable should all be the same length, and then it should all just work. I will put you in your breakout rooms while you are doing this thing. And I have some questions that I want you to consider after you have made this plot. All right, so discuss this among your team once you've made the plots. And they are, which has more bandwidth? And second, if these issues of electromagnetic interference matter more at higher frequencies, which of them is more likely to be affected by not accounting for EMI effects? Welcome back, everybody. Okay, so if you made these plots, you saw that the sine waves FFT looks kind of like this. It just has two spikes, one at the positive and one at the negative of the frequency of the sine wave. On the other hand, the square wave had all kinds of wild frequency content.
As a square wave is made of tons of different frequencies added together.
Yeah, it's made of all these harmonics. And I'm just bringing up my plot of that one for you too. There we go. And then the square wave, I'm plotting the absolute value of these things because that is a lot easier to look at. The square wave looks something like this. And these spiky harmonics continue out over a pretty wide bandwidth, but since we're looking with a limited frequency window, this is what we've got. So the questions that we were asked to consider is which one of these has more bandwidth? That one's pretty straightforward. Y does, because it physically takes up more, it has more support in the frequency domain. It just has content at more frequencies. And the second one was which one might be more affected by EMI and signal integrity concerns. That is also Y. And there's a couple reasons for this. You can have basically a few different things here. You can have an effect like dispersion on a transmission line, for instance. And that means that different frequencies go, we'll just say that they have different phase velocities and group velocities, although we haven't talked about that in this class. Different frequencies go different speeds, which can mean that instead of having a nice sharp square wave with nice corners, you might end up with something that looks kind of smeared out. Like that. Your rise and fall times tend to get wider because your sharp edges, the frequency content that controls the sharpness of your edges is the high frequency content of your square wave. And those sharp edges are getting smeared out by the fact that they're going at a different speed than the lower frequency content. So that's one thing that can happen. Another thing that can happen is, remember this picture that I drew? Let's say we have circuit 1 and circuit 2. If circuit 1 has a square wave on it, circuit 2, if there's any sort of mutual inductance between these things, then I can write that I on the current on circuit 2 due to circuit 1 is equal to that mutual inductance. Oh, I'm sorry, I did this wrong. This is a voltage. That mutual inductance times the time derivative of the current on circuit 1. The time derivative of a current that looks like this is a delta function train. So you can end up with this really spiky voltage waveform over here in response to this nearby square wave. This kind of thing happens a lot. And this is just because the high frequencies are the ones that contain the pointy features of your signal. And it makes it harder to, if your high frequency content gets distorted or messed up in some way, it makes it harder to distinguish a 1 from a 0. And if you have a lot of high frequency content, then it makes it more likely to talk to the circuit next door. So let's talk about this in a little bit more precise way. There are a lot of different kinds of of effects that sort of fall into this category of signal integrity. One of them, the first one I want to bring up, is electromagnetic interference. And that is one device emits a signal that affects another device. This could be conducted for instance, through like a power cable or something that is connected to both of them. Or a data connection or something like that. Conducted just means it is physically connected somehow. Or radiated. The difference between conducted EMI and something that is not EMI is that this is an undesired signal. Somehow, some signal from device number 1 gets into this data cable or gets into this power connection that is not supposed to be there. And then that makes it into device number 2 and is also not supposed to be in device number 2. And that's the difference between just physically connecting device number 1 to device number 2 through the data cable, and they talk to each other. That's fine. That's not EMI. So that's one thing. EMI is actually it has a regulatory definition. It's a term with specific procedures for how to measure it. So it can be, it's a good thing to be aware of. And if you design a device in your lifetime, you might need to think about EMI and design for its mitigation and then test for it. There are also transmission line effects, and there are a lot of those. Some of which are effects that can drive EMI, and some of which don't really. So you can have mismatch and reflection, which is a signal integrity issue because that depends on frequency, because some impedances, right, for an inductor, right? If I just write the impedance down for inductor, that's a J omega L. Well, that depends on frequency. So my reflection coefficient for something that involves an inductor is going to depend on frequency. Obviously, this can change the shape of your signal. That's a signal integrity issue. You can have a location where the transmission line shape changes. Like, for instance, if you had microstrip and the width changed or something like that. Other discontinuities on PCBs. These are really common when you have a situation where you really ought to be treating it like a transmission line circuit and you're not. So vias, where if this is your PCB and you have maybe one trace on this line and you want to connect it on this side, and you want to connect it to a different trace on the other side, and you have a via that goes through, just like a plated through hole on your PCB. This can also it can have reflections, it can have an inductance. It is not just a transparent continuation of this side onto this side, because if these behave like transmission lines, they're going to be really surprised by this. Electromagnetic waves don't like to be surprised. Any sort of transition, connectors, leads, adapters. These things are not transparent. Gaps in something like the ground plane or in your transmission line. And you can have coupling. Well, I would put this in a different section because that's not a discontinuity. So let me make some space below here. Coupling, that would be mutual inductance or capacitance from other transmission lines. All of these things are things that can have an effect on your signal integrity in a transmission line sort of point of view, especially when you have a circuit that undergoes transmission line effects, but you are not paying attention to them. That's all this stuff. I want to talk a little bit about this coupling thing, because this is where you might have heard the term crosstalk before. This is that. So let's talk about it. Which is actually coupling. You can have two transmission lines, let's say. I'll draw transmission line number 1 like this, and transmission line number 2 like this. And let's say that they both have a load, they both have a source with some sort of source impedance, and they're all connected up. They look great. If they're just like this and there's no coupling between them, it's fine. But if there is a mutual capacitance between these things, which is also sometimes referred to as a stray capacitance because it was not intentional, or a parasitic capacitance because it draws current from what ought to be existing on transmission line 1 and not affecting number 2, and it sort of pulls it to somewhere else. Then what you can have is there's some electric field that exists between these two lines. And so you'll have charges that build up down here and opposing charges over here. And then you can say that there's a current induced on transmission line number 2, which is equal to that mutual capacitance times the time derivative of current number 1. And these things are symmetric. So you can also have a current on circuit 1 due to a voltage on circuit 2. Can you steal power from power lines this way? I suppose you probably could, although usually they are designed to be fairly well shielded from that. But yeah, you could do that.
Would this explain why holding like a fluorescent light underneath the power line, like if you're just walking around, it can light up?
Yeah, exactly. That is the situation.
Like I've seen the YouTube videos of people demonstrating that.
You end up with a mutual capacitance or a mutual inductance developing between your fluorescent light and the power lines above. And the power lines have really high voltage. So there are really strong electric fields around there. And those electric fields are not completely confined between the two power lines, right? Because you've got lines that are like this, and the field is doing one of these. By the way, if anybody is not sure about what they're going to talk about for their applications of EM video, that would be a really cool thing to explain and maybe demonstrate. Walk around under some high power lines with a fluorescent light bulb and show us what it does and explain how it works. I'd be so excited. I already talked about mutual inductance, but this is the section where I would put that in too. So I'm going to draw a picture of that. Consider the same two transmission lines, right? Transmission line number 1. Transmission line number 2. And let's say this time that there is a strong magnetic field that isn't very well confined between the two wires of transmission line number 1. So maybe you end up with a situation like this. Do I have a different color of marker? My kids stole them all. Awesome. Oh no, they're over here. Cool. So let's say we have a magnetic field that's maybe doing that. And linking these two circuits. So then you can have a voltage on transmission line number 1 that is induced by the mutual inductance and the current on transmission line number 1. This is on 2 due to number 1. You can put some shielding on your transmission lines to mitigate these kinds of effects. You can also choose the type of transmission line that you use to mitigate this. For instance, coax actually does do a good job of containing the fields. That's what the electric field looks like, and then the magnetic field circulates around like this. And coax pretty much does confine the fields to the inside of the coax. So the only place you end up with issues on coax is at transitions, where maybe you connect a piece of coax to an antenna, right? So you connect the inner conductor to maybe the positive end of the antenna, and then the outer conductor to the bottom end of the antenna. This tends to invite and induce currents on the outside of the coax, which is not where you want the currents to exist. You only want them to be on the inside. This is a situation that as an antenna person, you have to mitigate a lot. So I think about it pretty frequently. And it introduces the whole concept of a balun, which is for transitioning between something with a ground and something that's supposed to be operated in a balanced way with a plus voltage on one end and an equal and opposite minus voltage on the other end. Anyway, that's a little bit outside the scope of this class, but it's a relevant concern also because these currents on the outside of your coax, or alternatively common mode currents, also a problem. I guess these are kind of the same thing sometimes. Common mode current is where on your transmission line, instead of having one current flowing this way and the other one flowing that way, so they're in a nice, well-behaved transmission line mode that doesn't radiate, sometimes they will do this and they'll both flow in the same direction, and then it does radiate, and then it is really not very well behaved at all. All of these things can happen. And this is one of those things, like I was talking to you just before about discontinuities in your transmission line causing unexpected effects. This is one of those. This is a discontinuity causing current to go where it's not supposed to go. So this is, I don't know, this is a weird class because all I'm doing here is telling you about weird things that can go wrong in your circuits. Another thing I want to bring up, and then we'll have, I think, time for an activity before the end of class. You can have switching noise. That, the square wave thing I talked about could be an example of this, because it is noise, really interference. In one circuit due to those transients in another. So you might end up with your ground voltage not being perfectly equal to 0. Because it is like the ground plane is a finite conductivity thing, and it has actually some inductance. So you can support a voltage across the ground. That could be a problem. Or you could have something draw a lot of current from your power supply, and then maybe your supply voltage drops because it intermittently draws a lot of current from there. So yeah, ground, non-zero L and R, inductance and resistance. And on a ground plane, the location and distance of things matters, and it matters more as frequency increases. Why is this? It's because remember when we calculated the resistance of just a cylindrical shape of finite conductivity? The length of it increased the resistance. So a longer distance of something with finite conductivity has higher resistance. Same thing with inductance. Remember when we calculated the inductance of a coil or something? You can also calculate the inductance of just a wire. And in general, length tends to increase inductance as well. When you are dealing with RF circuits, if you are wiring a circuit up, like in one of your labs in another class or something like that, and it has anything that is operating at a moderate to high frequency in it, right? If you think you might be hitting up against that lambda over 10, maybe we should think about transmission line effects, circuit size. Think about this. The magnetic flux contributes to induced EMF because of Faraday's law. So that means that any loop of wire in an RF circuit is an antenna unless you intentionally take care for it not to be. When you're like wiring a breadboard, any loops that stand up away from the breadboard can have a magnetic flux pass through them. So if your breadboard, for instance, if your breadboard looks like, maybe you have a chip on there, and then you have a big old loop of wire connecting the chip to something. Magnetic flux can go through there. So you can get currents induced on this thing from somewhere else, some other device, some other circuit, from like solar flares. Anything can happen. And if you have more than one chip on your circuit, and maybe you have a couple of loops that stand up parallel to each other, these can share magnetic flux. And now you have a current pathway that is bypassing your circuit entirely. That this is going to create an inductance that's just going to bypass chunks of your circuit. So what should you do? Keep loops small. Lay them flat against the ground plane or some other piece of metal. If you absolutely must have loops, like if you have two inductors, position them perpendicular to each other. This will keep your wires from unintentionally talking to each other. This is really an important thing, and it really helps with circuit troubleshooting. When you have something where maybe you're measuring the circuit, but the signal just looks really noisy for some reason, just like take these little loops and fold them down against the ground plane so they lay like that instead of standing up. Because then the area of the loop is so much smaller and not very much magnetic field can go through it. There's no field on the ground plane. This brings up the last thing, and also maybe a brief activity that we can sort of speculate about as a class for the last couple minutes. Solar storms Does anybody know what solar storms do?
Aren't those the things that happen when like the sun shoots out like a flare that creates like a loop on the sun?
Yeah. And what does it do to the solar magnetic field?
Like the Carrington event of 18, like 50 something.
That is what I'm talking about. Yes. Do you want to tell people what that event was about?
Um, so I think there was a solar flare, which is an emission of charged solar particles, more so than normal. Normally, the Earth's ionosphere, I guess, due to the iron core in the Earth rotating, which creates a magnetic field around the Earth, protects us from those charged particles. But there was just so much that it overwhelmed that. So it pretty much induced a lot of charges within all the telegraph wires on Earth. And apparently it was so strong that just touching telegraph wires would like shock you. They were warm to the touch, and people could actually use them without any power at all over like miles and miles. They actually worked better if they disconnected the batteries from their like 100-mile long telegraph wires, just because of the induced current on the wires from the solar radiation. And if it also like fried a lot of the wires. So luckily we were only using telegraph wires in the mid to late 1800s. But if it was, now, that would be disastrous.
Yeah, what on earth could happen to an electronic circuit during a magnetic storm of that magnitude? On the other hand, um, telegraph wires have the major disadvantage that they were hundreds of miles long, right? So imagine the area of that loop. If you have something that's maybe just a few centimeters in size, maybe it'll be fine, or maybe it is not really designed to accept the amount of EMF that would be induced by a geomagnetic storm of that magnitude. This would also make a really good applications of EM video. There's so many cool things to dig into here, and I'm kind of sad that it's our last day because any one of these things could be a really interesting lecture topic. It could be a week, it could be a project. There's a lot of stuff to talk about here. Anyway, that's cool. Is our last couple of minutes of class, so I want to remind you again about the announcements that I made at the beginning because I think we had a couple people who joined late. One, Wednesday is going to be a review class. Bring your questions. If you want to do a problem out of the book, if you have a question in mind that you would like to work out together, if you just have a topic that you'd maybe like to have some review on, let me know. Second, exam format. It's a take home. You will have the full week. No time limit. Except of course for the week. Because I don't think that worked very well last time. Oh, can you work on the EM videos with a partner or in a group? I hadn't thought about that. Are there people who would want to?
Yes.
Okay, go for it. I don't mind. That sounds fine. One more thing I wanted to say about the exam format, and I forgot. Oh yeah, it's going to be a single file upload, and you're going to need a Smith chart. So if you can't print one, please send me an email and I will mail you one. I'll just like drop it in the mail today and you'll get one in time and it'll be fine. In fact, I'll mail you 10 so you have some for scratch. We talked about which chapters are going to be on there, and it's basically everything 2 through 8. So we got the superposition laws, we got the flux laws. Actually, no, it's not going to work that way, Michael. He asked once we start the exam, do you have to finish it at the same time? No, you only get one submission, but it's just going to be, it's not going to be inside the quiz. It's going to be in the assignment section. So you'll be able to see the whole thing at once, and you'll just be able to work through it for the whole week. And you can leave and come back and then upload the file when you are finished with it. That means, though, that by the end of the week, you must upload something, because I'm not going to accept late submissions. Got it? All right. We had path laws. We had Max and Faraday and plane waves. Then we had a lot of stuff on transmission lines, 2 chapters on those, 6 and 7, and Smith charts. And then we had antennas. We learned a lot of stuff. And I know I've talked about it a lot today, but don't forget the video. It is due the 17th, which is in a week. Do people feel like that's enough time? I'd prefer to leave it there so that you can just concentrate on the exam. I'm going to post it on Sunday, the exam. So, yeah.
Professor,
Yeah.
so is it going to be posted Sunday and do the following Sunday?
Yeah.
Okay, thank you.
It sounds like people want more time for the video. I will just make it due at the same time as the exam. I didn't really want them to overlap, but it sounds like people would prefer that. So I'm happy to do that. We can just work with whatever your schedule is. And that is it. I'll see you Wednesday. Don't forget
Professor,
to keep an eye out for those course values. What?
how many people per group for the for the EM video?
Not more than 3.
Okay, thank you.
Cool. I am not going to stick around today because I have to run an errand between my 2 classes. But if you have questions, you can stop by office hours later on Wednesday or email me. I'll see you later. Bye, everyone.
Bye, thank you.
See you later, Professor.